This video deals with the motion of photons in the equatorial plane of the Kerr geometry. It begins by looking at how the world line and form momentum of a photon can be parametrized and uses this result to generate the equation that governs the motion of these particles in the equatorial plane. This equation of motion contains the effective potential that provides further information on the motion of these particles. So basically I'm going to parameterize the for velocity and for momentum of a photon, and then look at its equation of motion in the vicinity of a Kerr rotating black hole. All right, so the problem of the motion of massless particles near Kerr black holes is in general complex, but can be made more tractable by considering the case of motion in the equatorial plane. It's exactly what we've done in previous videos with massive particles. We made use of the symmetry of the equatorial plane and some Killing vectors in the time and azimuthal angular momentum directions. So in this plane, we choose theta as pi on 2 in the equatorial plane, and we're going to set the theta component, the polar component of angular momentum, to 0, so the particle stays in the equatorial plane only. Now let's first look at the motion of these particles that include photons, gravitons, and possibly some neutrinos. Right. We can't parameterize the path of these particles using proper time, since d tau equals 0 between any two events on such a particle's world lines. So we can't use proper time, because between any two events, the proper time elapsed d tau is 0. Now, in some arbitrary inertial frame, okay, non-accelerating frame, we can describe the path of a light ray traveling along the x-axis to be x equals ct. So on this space-time diagram, with the y and z directions suppressed, we can see the world line of a photon is x equals ct. Okay, the world line of this light ray can be described with its coordinates. So its position 4 vector is ct xyz is ct 0, 0. Remember, x equals ct. All right, and the motion is only along the x-axis. So the y and z components are 0. Now here the parameter we're using is lambda. This is our affine parameter. Lambda equals c times t. And when I say affine, it just means we can take this parameter, we can multiply by another scalar, or we can multiply by a scalar and add or subtract a constant, whatever. That's the nature of it. That is what's meant by an affine parameter. So we're going to use this parameter. We're not going to use squares of this or cubes or any other powers of this. We're just using lambda, and any sort of linear combination of other scalars with it also works. So lambda is ct. Now we can write this parametrically in the form of x mu equals u mu lambda. This u mu are the components of a constant tangent vector, which is the for velocity. All right, so here u mu has components 1, 1, 0, 0. X dot mu is, and x dot mu is dx mu d lambda equals u mu. So that's how we go from the position 4 vector to this vector u. It's the derivative of these components, okay, gives us this constant vector here. The tangent 4 vector to this world line is u equals x dot mu e mu, so expanding it out the basis. I can't show, obviously, on this diagram the time axis. I can't show time. But it's only a visual image. Okay, but what's happening is that in the in space-time, this vector here, this 4 vector u, is parallel transported along this curve. And the parallel transporting means that the magnitude and the direction of the vector is kept constant. Anyway, so we have this tangent vector here, u is x dot mu e mu equals u mu e mu, okay, where u mu are constant components. All right, now what's important here for massless particles is that this is a null vector. All right, so the scalar product or the inner product of the for velocity of this particle with itself, u dot u, is eta mu nu x dot nu, okay, or eta mu nu u nu, and expanding that out, there's only two terms, the 0, 0 and the 1, 1 term. It's a diagonal metric with constants. Eta 0, 0 is -1, and the spatial parts are 1, at least on this channel anyway. And so we have a negative here, 1 by 1 plus 1 by 1 is 0. So this is a null vector because its magnitude is 0, magnitude squared is 0, or its magnitude is just 0, square root of 0, 0. So the world line is a null curve. So massless particles are traveling along a null curve because the tangent vector to this null curve is also a null vector. So a null curve has a null vector as its tangent, or the tangents to a null curve are null vectors. And the equation of motion of the photon is given by this. du d lambda is 0, okay? So this u is a constant vector. Its derivative with respect to the parameter is 0. Remember, with parallel transport, a vector's magnitude and direction is held constant, and it's parallel transported along the curve parallel to itself. And that's achieved by keeping the magnitude and direction constant. Now, this is a vector equation, and since vectors are tensors, we then know that this equation holds true in all coordinate systems. Now, before I move on, just a short note about coordinates. We are free to rescale coordinates as necessary. So we can take the radial coordinate r, multiply it by some scalar factor alpha to produce a new radial coordinate, r bar, let's say, is equal to alpha times r, and we still have a radial coordinate. However we rescale it, we still have a radial coordinate. All right? And once we've rescaled it, we can drop the bar bit there and just call it r, this the new r. Okay, we're free to rescale our coordinates as we choose. Right. We can still differentiate this radial coordinate the usual way, so differentiating it with respect to the parameter lambda. dr bar d lambda is just alpha times dr d lambda. We can represent the form momentum of a photon by rescaling the null vector found on the previous slide, so taking the form velocity and rescaling it by multiplying it by some scalar alpha. So our form momentum can be represented as some scalar alpha multiplied by the form velocity. So P is alpha u, or earlier from the coordinates we were talking about, alpha x dot mu e mu, expanding it out in the basis vectors e mu. This is also a null vector since P dot P, or the inner product of P with itself, is the contraction of P with itself is alpha u is alpha squared u dot u. We know u dot u is 0 already, so that takes this scalar product to 0. Writing that out with the coordinates earlier, coordinate notation earlier, P dot P is alpha squared eta mu nu x dot nu, okay, is equal to 0. Now, we can choose this scalar alpha such that the components of this form momentum vector in some arbitrary inertial frame are, I should have had squares on these. My apologies. I should have had squares on those. And then what I'm trying to get at there is this is E is equal to P times C. All right, so E is P on C. And so we have this, if you remember, this constant in the first place, constant in the second place, okay, 0, 0 elsewhere. So it doesn't change. If you put E equals PC into here, C's cancelling, you've got P, P. All right. So all we've done is taken the form velocity, multiplied by a scalar, and we get the form momentum. All right. More commonly, the four-wave vector is used to represent the form momentum in the form P equals h bar k, the four-wave vector. And here there's different representation. I'll take this one. P, the components P mu is h bar, k mu is h bar times then omega on c, the frequency, and then omega on c, and this unit normal vector, unit vector perpendicular to the wavefront itself, and where the magnitude of this unit vector is, of course, 1. Now, turning now to the motion of photons in the Kerr geometry, we now go from the flat space metric to the curved space metric, g mu nu, and the inner product of itself, or the contraction of the form momentum vector with itself, is g mu nu. P nu is this up and index load. I should have put a mu there. I made a slight error. Sorry, people. It should be mu there. They should both be the same. My apologies. Which is the same as g mu nu p nu equals 0. Now in the equatorial plane we have theta as pi on 2 and p theta, the polar component of momentum, polar angle component of momentum is 0 because we want to be in the equatorial plane. So we drop all that. What we're going to do is expand this expression here for each of the coordinates t, r, theta, sorry, not theta, and phi. So t, r, and phi, and no theta. All right, so we get GTT is this, GTT, PT, PT, 2 GT phi, PT, P phi. There's two of them because of the cross terms. We have GRR, PR squared plus G phi phi, P phi squared, okay, G phi phi, P phi, P phi. That's all equal to 0. And what we'd like to do now is we're going to, as we did with the massive particles, rearrange this expression to put this on the left-hand side and put everything else on the right. Okay, so we're going to transpose everything onto the right. And here we go. So from a previous video for motion of particles in this plane, we found that PT was minus E on C, P phi was the angular momentum. This is the angular momentum of the particle in question, in our case the photon today. The covariant form of the momentum component is GRR R dot. R dot is the contravariant component, and GRR is 1 on GRR. Okay, putting those in. So here's our expression from the previous slide. Okay, putting that in like that. So substituting those in, this PR term becomes this. We have all these, PT is minus E on C and so on. P phi was H. And then here, this is GRR squared. And this contravariant term here, this inverse metric term here, cancelled one of these. So we're left with this. Then we multiply through by the inverse metric term again to get all this. Now also from the previous video, we have these inverse metric terms. Those, and we're going to substitute those in as well. So when we do that, GRR here, the inverse metric component for the GRR is delta on R squared. Put that in here, putting that out. Now these deltas are all going to cancel, and some minus terms here will cancel. This will become negative, this is negative. So we end up with all of this. Okay, and we're getting closer to what we'd like to achieve, but if we could express this in terms of this E on C in terms of some other energy parameters, what it is, we'll do that, and that's what we'll have a look at next. Okay, so we're getting closer to the equation of motion of photons in the equatorial plane, but we'd like to deal with the E on C term. So to do that, let's imagine some observer at rest at infinity whose fall velocity is given by u mu. So far from the source mass, the flat space metric applies, and the fall velocity of the stationary observer here, with or without the flat space metric, the far from the source, the fall velocity of the observer, of some observer at rest at infinity is this. Now a photon traveling in the positive direction of some x-axis passes this observer. So you've got this photon passing the observer on the right, towards their right, positive x direction, headed off towards the source mass. And so the observer, passes this observer with a form momentum. This is the photon's form momentum, is these factors here, c times epsilon. This epsilon turns out to be the energy parameter, c epsilon 0, 0, and because it's moving down the x-axis. And the covariant form of this will be using the flat space metric. Since as r approaches infinity, the flat space metric becomes applicable. So lowering that just puts a minus sign here. This observer then measures the energy of the passing photon at their location, at the instant it passes their location, to be E equals minus P mu U mu minus P0 C equals minus epsilon C times C. Okay, P0 here is this minus C epsilon, okay, and this U0 term here was just this plus C. So that's how they've come about. Two minuses cancel, we get epsilon times C squared is equal to the energy measured by the observer. Okay, so let's form the ratio epsilon as E on C squared, and that tells us that E over C is equal to C times epsilon. So we have an expression now for E over C in terms of C times epsilon, and where epsilon is just an energy parameter that we've used previously. Okay, so we insert this into our previous result, and the last line on the second last slide there was this, and where E on C is, we'll put C times epsilon. Okay, and then what we'll do is expand all that out, and then we'll collect like terms here. That's the ones over R squared, and the ones over C squared R cubed. Okay, and then we'll factorize that quadratic there, and it produces this expression. So R dot square, the equation of motion, or the radial component of motion there, is equal to all this. This is looking like the energy of the orbit. This is looking like the effective potential term, and this is looking like the kinetic term. Okay, now we know that there'll be no purely radial geodesics in the Kerr geometry. Also, there'll be a range of scattering, deflection. There's no purely radial geodesics because of the frame dragging effect. So even light is forced to rotate with the source mass once it gets close enough, even if the light is in a counter-rotating orbit to begin with. So we know that there's going to be no purely radial geodesics. We also know there's going to be a range of scattering, deflection orbits, as well as plunge, fallback, and a variety of precessing orbits. So maybe we should be looking to work perhaps with a impact parameter. I mean, you can imagine a light ray coming here, passing through the source mass, missing it on a scattering orbit or in a deflection orbit, okay, or maybe in some sort of closed orbit. So maybe it's useful to work with an impact parameter, and just as we did in the Schwarzschild case. Now, so we're going to take an impact parameter we'll call B. This variable takes the form of B is the angular momentum of the particle involved, not of the black hole, but of the particle itself, over the energy parameter times C. And so that means 1 over B is the reciprocal of that, C times the energy parameter over H. All right, now in the limit R approaches infinity, this variable B acts like an impact parameter. You can imagine a light ray coming from here off to the right, far from the right, okay, passing the mass. So this value here you could describe as an impact parameter. Now, next step is we seek the form of the effective potential just as we did for the Schwarzschild geometry. So it's coming back to our energy type equation here. Okay, let's divide through by H squared, everything. There we go there. Okay, when we do that, this C squared epsilon squared over H squared is really just 1 over B squared. That's good. Here we've got C squared epsilon squared divided H squared times A squared. So that's just A squared over B squared. H squared over H squared is just 1. Over here, we've got this part here in the numerator divided by H squared. Okay, so we can rewrite that as H minus A C epsilon on H all squared. And keep going. Okay, so that gives us then, so repeating that last line here we are. Okay, well now we have 1 over B squared, we have this here, plus here, we can see that H over H is 1, A times C epsilon over H is A over B, all squared. Next thing we'd like to do is just repeating that last line, so as not to rush anybody here. R dot squared over H squared is this. Okay, and then what I'm going to do now is this 1 over B squared looks like a constant, looks like an energy term. So I'll leave that on the right. And these next two terms I'll transpose to the left-hand side over here. Okay, and then just one more step here. I'll factor out a -1 from these parentheses here. This makes that a plus. I'm left with all of this, which looks very much like R dot squared over H squared plus the effective potential as a function of R and B, the parameter B, is equal to 1 over B squared. A little bit of caution needs to be taken with respect to this so-called effective potential. Okay, so our effective potential for the motion of photons in the equatorial plane is given by this object here. Okay, now a note of caution, my apologies, a note of caution when interpreting this as an effective potential. We form this expression for V effective from R dot squared over H squared plus VF equals 1 on V squared, and not from its usual form R dot squared plus V effective plus this energy term here. Because within this term here, this 1 over B squared term, normally the usual form of this energy equation has an energy, the total energy of the orbit over here, the effective potential, and then the kinetic part here. Okay. Now in the former term on the right, the 1 on V squared, it's C times epsilon, that's energy, over angular momentum, all squared. While in the latter, the term on the right is an energy term only. This one here is the energy term only. All right. Now the latter form, that's this one here, is consistent with the familiar kinetic energy plus effective potential equals total energy of the orbit, while the former E part of the equation has a dependence on the particle's angular momentum h. See over here, what should be the E term, the capital E term, total energy, has a dependence on both the angular momentum and the energy. So it's not really in that traditional form. So there's a bit of a note of caution there when interpreting this whole thing as an effective potential. All right, just be aware of that. All right. Another thing too, we are free to remove the explicit dependence on h in our previous equations through a rescaling of the affine parameter lambda in the form of replacing lambda with h times lambda to produce a new affine parameter. Okay, perhaps lambda prime or something. So we can absorb the h into the affine parameter lambda, okay, to produce a new parameter. All right, now using the following values, g, the gravitational constant, the mass of the black hole, the speed of light, set those to 1, and using the dimensionless spin parameter, which I haven't labeled dimensional spin parameter, but that's what it really is 0.8. A plot is shown below for b equals -4 and +4. Now, +4 means prograde, means the particle is rotating in the same direction as the spin of the black hole. -4 means it's rotating with 4 units of angular momentum per unit of mass in the negative direction, or opposite or counter rotating with respect to the black hole. Okay, so positive for prograde, negative for retrograde motion. Okay, so B equals -4, the retrograde motion gives an effective potential plot like this, very similar to what we had for the Schwarzschild case. And for the prograde case, B equals +4, we get this effective potential here. This is the effective potential plotted here with these constants set to 1 and A is 0.8. Okay, and it's plotted for 2 values of B. +4 prograde, that's the particle rotating with in the same direction as that of the black hole, and retrograde -4 for the motion of the particle rotating against the rotation of the black hole, counter rotating. All right, notice here there's no local minimums on any of these. This plot here just asymptotically approaches the horizontal axis. There's one local minimums, which we recognize as being the location of an unstable, very important, unstable circular orbit, unstable. All right, the unstable circular orbits occur at these points here, these local maximums. R is 2 in the case of the prograde case, and R is 4.5. When I say R is 4.5, I mean 4.5 gm on c squared, or 2 gm on c squared in this case here, okay? Just rescaled the plot to keep the numbers simple. And here's the effective potential that's been plotted here. These are points of unstable circular orbits. Now, as in the Schwarzschild case, there are no stable circular orbits in the equatorial plane of the Kerr geometry, since no local minimums exist. Now, in the limit that A approaches 0, as the spin of the black hole approaches 0, we recover the Schwarzschild effective potential for photons. So this becomes, in the limit A approaches 0, it becomes this object here. All right. Okay. notice there's no explicit H squared, no H dependency in this effective potential. There's no angular momentum of the particles explicitly appearing in the effective potential here. Okay, notice that H is not explicitly present here in the Schwarzschild case, as they've been absorbed into the impact parameter. Remember, in formulating the impact parameter, we absorb that angular momentum term. But normally, in general, in the Schwarzschild geometry, when dealing with photons, the energy equation has this form, where the H explicitly appears and the total energy over here. Okay, so the effective potential becomes H squared on R squared times all that. All right. When we resort to using the impact parameter, this H squared is absorbed into the impact parameter. But then the effective potential that's produced, you need to be careful in interpreting it. All right, that's it.